Now let's think about the bandwidth of the amplifier, and we have talked this about before. Let me show the next slide. So here what you see is a 3-level laser, and the lasing frequency is the transmission of the electrons from the level 3 to 2. That means the laser is working at from 3 to 2 transition. So what you do for this, of course, first you pump the laser, you pump the medium, the gain medium or the amplifier, so that its ground state electrons jumps to this excited level 3 energy level of the excited second excited state. Let me talk about this. 1 is the ground state, 2 is the first excited state, and the 3 is second excited state. And when the electrons jumps to the energy level 3, then the condition for the population inversion is already satisfied, because there are no electrons in the second energy level, so that N3 is larger than N2. Then we have the condition for the lasing satisfied, the first condition. And in that case, if there are other atoms just doing this transition from 3 to 2, then they will just radiate photons of energy frequency that matches to the energy transition between 3 to. Then this photon will just stimulate the nearby atoms to drop their electrons in the third level to the second level. Okay, thereby the amount of number of atoms in the medium or in the resonator will increase. So that what you see in this picture, that if there is initially some amount of photons or some amplitude of light, this light will get amplified. Okay, but what you see over here is that the intensity frequency graph, we will see this intensity increase because of the stimulated emission when the frequency frequency of photons is just at this special frequency f32. Well, f32 is nothing but E3 minus E2 divided by h, the Planck constant. So, but you might expect that this peak, must be sharply shown in the graph. And the graph, you might expect that such a graph, and we have this horizontal axis, the frequency, and this is the intensity, and this is f32, right? So why do we have such a bandwidth? This is the first question. That means even if the frequency is not exactly at this value, okay, even the frequency of the photons are not at exactly this value, still there will be some stimulated emission. Okay, so what does that mean is that as if something something about the exact position of the energies E3 and E2, right? It looks like E3 is not sharp over here, but it is some kind of let's say uncertainty around this sharp level, and some kind of delta E is there, okay, delta E3, and similarly some kind of delta E2 around this sharp line. Okay, well, the reason that you see this no any sharp increase in the intensity but some bell-shaped like increase would be when you think that these energy levels are not sharp. Okay, these energy levels are not sharp. Well, what's the reason for this? One reason that the energy levels in the atom is having not, sharp values, but some kind of, noise around some sharp value or some kind of uncertainty, will be having some different, let's say, causes. The first thing is that the atoms inside this amplifier medium, they are not fixed, okay? They are able to just vibrate, because if this is a solid medium, if you have a crystal inside your resonator between these two mirrors, the crystal, first of all, it's that it's a transparent medium that the light is coming and passing, transmitting through the medium, so that it will get amplified. But the thing is that when you think about these crystal atoms, they are not at one fixed position, and as if they're not changing their location at all. We have some kind of model for solids that even if the solid is like very hard like crystal, the atoms may just vibrate in their original position. And because of this vibration, these energy uncertainties may occur, right? And one reason is that when an atom is not a fixed position in space, let's say if it's moving, then, and while moving, there is absorption or emission. Well, since we're talking about the emission over here, is that while a moving atom in with some direction is moving, if emits light in this direction, or in this direction, whatever, but if an atom emits light while it's moving in a certain direction, the emitted frequency of the light depends on the direction of the motion of the atom. If, for example, if the atom is moving in this direction and it is emitting light in just the opposite direction, let's say these transmission because of the atom's 3-to-2 levels, and also think about the emission of the photon in the direction of the atom motion. So you might think that there is no any difference between the frequencies of these emitted photons in different directions, but in fact there is. And if you have heard about Doppler shift, and you know what I mean. If the atom is moving in this direction, and if it radiates a photon from the 3-to-2 transition, the frequency of this emitted photon will look like larger than F23, but it's not very much. It's slightly larger. And in that case we say that this emitted atom is blue shifted, okay? But if while the atom is moving in this direction, if the radiation if the photon radiated is going in the opposite direction, then the frequency of that photon is going to be a little smaller than F32. Okay, let me put these larger so that you can see F32. So and this is because I said because of the Doppler shift, and this is something you experience in fact in daily life. It is not only unique to waves like light waves, but it's observed in sound waves. And this is what you observe in, for example, if you just nearby a railway, and there's a train coming towards you, and if the train is just honking, it's just if it's producing sound, then the sound coming from the train is going to be like a thin sound, like pitch. It's a low pitch. Sorry, it's a high pitch. And when it's approaching to you, the sound looks like a high pitch sound, but when just passes near from you and then goes away from you, then the sound coming from the train will change to a lower pitch sound. Okay, and this is called Doppler shift, because while the train is approaching you, the frequency of the sound wave looks like larger than original source, while if the train were just standing at rest, whatever the frequency of the sound, it will be the sound that for coming from the train which is moving toward you is going to have a larger frequency. But as I said, this difference is not gonna be very much, so it's going to be very little. It corresponds to this case, while the train is just going away from you, okay, and the sound coming from the train, the frequency of the sound coming from the train is going to be less than the original frequency. So this is called Doppler shift, and it's, as I said, it's not unique to sound waves. It's also true for the light waves or light frequencies. So in fact, this is the physical phenomena that we use to find the expansion of the universe. The universe is expanding, and we know this from the light frequency shift coming from very far distant stars, and they observed that the stars, in fact, they radiate at a certain frequency of light if they were just standing there or not changing their distance to us. But since they're changing their distance, or they're just moving away from us in every direction, when you look at around in the sky, and all of the stars are looks like they are going away from us. Okay, that's because of the expansion of the universe, and this we know from the frequency shift of the light coming from these stars, and these frequency shifts are just red shifted. This is red shift, and this case is called blue shift. Okay. So when this is the case, what happens that this sharp line becomes a bell-shaped line, okay? Because while the atoms are vibrating or moving in some direction, well, you may look like this picture as if the medium is a gaseous atoms, but even if the medium is a crystal, and the atoms will still move, or they will vibrate in all possible directions. Even this vibration motion will cause these shifts. Okay, so then in that case there will be a shift, and this sharp line of transition becomes a bell-shaped line. Okay, that's why we have some bandwidth of around this resonant frequency. Okay, so as I said, there might be some different causes, and one cause is because that this Doppler shift, let me erase this part. Okay, one cause is because of this Doppler shift. That's what you see over here. It is the third item, and I just explained the Doppler shift. The other causes is that if particularly if you have an active medium, or the amplifier medium consists of a gas of atoms, these atoms may collide with each other, or they may collide with the container, or etc. And these collisions will further make the bandwidth wider. Okay, and one cause comes from the Doppler, and the other this is because of the motion of the atoms. Motion. It is because of the motion of atoms in the amplifier medium. Okay, and collisions, as the name suggests, this is because of the collisions of atoms in the amplifier medium. And the other cause is, even if there is nothing, no any collision, no Doppler shift, this bandwidth widening is because of the spontaneous emission. Okay, you know, if as I said, inside this resonator or between the two mirrors, I said there are two ways of emitting photons from these amplifier atoms. One is spontaneous emission and the other is stimulated emission. But what we are discussing over here, this sharp line occurring in the stimulated emission, even the laser is lasing, still there are some, even if the number is small, there are some atoms that they radiate their photons spontaneously in some other directions, not the directions in the direction of the laser, in the direction of the optical axis of the resonator, but in some other directions, that because they are emitting spontaneously. So even if there is nothing else, and there is still spontaneous emission, so there will be some bandwidth or some widening of the sharp line around this resonant frequency. Okay. All right. So this is all about, as the time being, there are three major causes in order to see, as I said, this originally might look like the intensity and the frequency, and there will be like some amount of light, but there will be very sharp increase in the intensity right at the resonant frequency. But as I said, this line is not going to be infinitely narrow. It's going to be like some width around this sharp line, and the reason for this is these three processes.